Hello everyone, it's great to see you again. In this video, F5M will show you that the colors you see every day don't actually exist. And we'll also answer the question, why have scientists never found a green or purple star? Let's begin. What do you think color really is? You might not believe this, but color doesn't exist in nature. The color of an object is described using properties like hue, lightness, and saturation. In reality, color is simply a perception created by the brain based on the interaction between light, which is electromagnetic radiation, and the light receptors in our eyes, specifically cone and rod cells. The sun is the closest star to you and me. At its core, the sun is a massive nuclear reactor. Every second, it fuses about 600 million tons of hydrogen into helium. In the process, roughly 4 million tons of matter, equivalent to around 800,000 adult elephants, are converted into pure energy through the equation E equals mc squared. A tiny fraction of that energy reaches Earth as solar radiation. Solar radiation is part of electromagnetic radiation, basically a collection of waves in the electromagnetic field. Each type of wave has a specific wavelength. Wavelength is the spatial period of a wave, the distance over which the wave pattern repeats. The wavelengths of electromagnetic radiation range from about 1 picometer for gamma rays to 100,000 kilometers for extremely low-frequency radio waves. In a vacuum, electromagnetic radiation travels at the speed of light about 300,000 kilometers per second. That means a wave with a wavelength of 100,000 kilometers completes just 3 cycles per second, giving it a frequency of 3 hertz. By dividing the distance light travels in 1 second by the wavelength, we get the frequency, and the full range of these frequencies is called the electromagnetic spectrum. The electromagnetic spectrum stretches from 3 hertz, or 3 cycles per second, at extremely low-frequency radio waves, all the way up to 300 exahertz, 300 quintillion cycles per second, at gamma rays. The higher the frequency, the more energy the wave carries, and the more dangerous it can be to living organisms. You can think of the electromagnetic spectrum like a ribbon. One end is gamma rays with ultra-short wavelengths, and the other end is ultra-long wavelengths, ending with extremely low-frequency radio waves. Somewhere along that ribbon, in the frequency range from about 430 to 750 terahertz, corresponding to wavelengths between roughly 400 and 700 nanometers, lies visible light, the part of the electromagnetic spectrum that human eyes can see. At one edge of visible light, beyond violet, is ultraviolet radiation. At the other edge, beyond red, is infrared radiation. When sunlight shines on an apple, most visible wavelengths are absorbed by its skin, while the remaining wavelengths are reflected into your eyes and translated by your brain into color. Which means the color of the apple, of you, of me, and of everything in the universe actually exists only inside our heads. In other words, the colorful world we experience is, at its core, just the result of a kind of mental filter that humans accidentally evolved. That's it. Now let's return to the question. Why do we see white, yellow, red, and blue stars, but not green or purple ones? When scientists analyze the light emitted by stars, they find that depending on surface temperature, a star's visible spectrum is dominated by a particular wavelength, the wavelength where the star emits the most light, called the peak wavelength. The University of Colorado provides an interactive simulation showing the peak wavelengths of stars at different surface temperatures. As you can see, hotter stars appear bluer, while cooler stars appear white, yellow, orange, red, and eventually deep red. In that simulation, the sun appears slightly yellow-white. Does that mean the simulation is wrong? No. Pale yellow-white is actually the sun's true color, not pure white, as astronauts often see from the International Space Station. That's because a star doesn't emit radiation at just one wavelength, corresponding to a single color, like yellow, orange, blue, or red. Instead, it emits across a very wide range of wavelengths, including the entire visible spectrum. And we all know that combining all colors produces white. White light essentially washes out the dominant color of a star when observed by the human eye. For the sun, its peak wavelength in the visible spectrum actually falls in the green region. However, the green band is quite narrow. so the amount of green light produced is relatively small. Meanwhile, red light, even though it doesn't sit exactly at the peak wavelength, spans a much wider band, so it's produced in much larger amounts. The mixture of a little green, a little yellow, a little blue, a little violet, and a lot of red, along with other colors, blends together into white with a slight yellow tint. The human eye isn't sensitive enough to detect that subtle yellow, so we usually interpret it as white. For the human eye to see a green star, that star would need to emit almost exclusively green light, and that simply doesn't happen in the universe. As for purple, a star with a peak wavelength in the violet range would also emit a lot of blue light, and when those two mix, our eyes tend to perceive blue instead. That's because, through evolution, the light-sensitive cells in our eyes became more sensitive to blue light than to violet light. This is also why Earth's daytime sky appears blue rather than purple. Violet light is scattered more strongly in Earth's atmosphere than blue light. Now, what about distance? Does the color of a star change depending on how far away it is? The answer is no. A green traffic light doesn't look greener when you walk closer to it, or less green when you walk farther away. Stars behave the same way. In theory, the Doppler effect can shift the color of light from stars that are moving toward or away from us. However, calculations show that this shift is so small that it's essentially negligible. It's also worth noting that in most images and videos of space, star colors are either artificially enhanced or recolored entirely to improve visual appeal or to better illustrate surface temperatures. If you enjoyed this video, don't forget to like and share. And be sure to subscribe and hit the bell so you don't miss any future videos from F5M. See you next time!